So welcome to Unit 5. Today we talk about actual robot motion. In the previous unit we talked about how to find paths. Now we'll talk about how to turn these paths into actual motion commands. In particular, we talk about generating smooth paths, and then we talk about control. In particular, a method called PID control. And as usual, you get a chance to program all these wonderful things. You might remember that our planning took place in a discrete world, and the type plans we found looked very much like this, perhaps in response to obstacles over here. Now, a path like this has lots of disadvantages. You don't want a robot to go straight, take a 90-degree turn, and go straight again. For one, a car can't even do this. But for another, this will force the robot to move really slowly around the corner over here. A much better path would look like this. This is a smoother path. In the extreme case, you might even generate a path just like this. So the question becomes, can we modify the blue path to look more like the red or the green path? So suppose you're a car-like robot right over here, and you wish to get to right over here. Which path would you prefer? The blue path, the red one, or the green one? Just check one of the three. And this is a question where I check your intuition. This is not a mathematically precise question. And the answer is subtle. I would actually prefer the red path. And the reason is, as the robot is facing to the right side over here, it can't take a 45-degree turn and enter the green path. It should slowly move around the corner, go down here, and slowly move to the right. The green path might be shorter, but it requires two 45-degree instantaneous turns, which isn't feasible for the robot. So to some extent, we'd like to find smooth paths that are executable by the robot.
As Sebastian mentions in this lesson, control is such a vast field. Engineers have been working on control theory for at least 100 years, and there is so much to learn. Coming up, Sebastian will teach you about PID control. PID is the most common controller in the world, and for two reasons. It works well, and it's really easy to understand and code. However, there are other types of controllers that work well in different scenarios, particularly when it comes to cars. Often these controllers involve building mathematical models of how a vehicle moves through the world. Students in the nanodegree program use this simulator to test out their control algorithms and validate how their vehicle moves through the world. Access to these simulators is a huge benefit for students since they help you visualize how your code moves the car and where your code breaks. Take a look at the nanodegree program if you're interested in diving deeper into control theory and predicting what your self-driving car will do in the future.
So in the path planning class, we specified paths as a sequence of points in a 2D grid, just like this over here. For the smoothing purposes, we will call each point xi. So this is a sequence that goes from x0 to xn-1. And each of these x's is really a two-dimensional coordinate, but that should be immaterial to the smoothing. You can do this in 1D, 2D, or 3D. So here's the smoothing algorithm. Initially, we create variables yi that are the same as all the xi's. Remember, these are the non-smooth locations that the planner has found. And then we optimize two criteria. The first is we're minimizing this expression over here, and the second looks as follows. So in the first sum, we minimize the error of the ith original point with the ith smooth point. In the second, we minimize the distance between consecutive smooth points, both to the square. So here's a little quiz. If we only apply the first criterion, so forget about the second one, will we get the original path, a smooth path, or no path? Please check exactly one of those boxes. And the answer is, if we just optimize this one over here, we get the original path, and the reason is obvious. It's already 0 for the original setting, so further minimization doesn't make it any smaller. It's a quadratic arrow. The minimization has no effect, we just get the original path. Now let me ask the exact same question just for the second criterion, so forget about the first one. What happens if you only optimize this criterion over here? Do we get the original path, smooth path, or no path? And the answer here is you get no path. This criterion alone asks that all the y's are as similar as possible. It's minimized when all the y's are the same, which means you only get a single point and we get no path at all. So obviously these two criteria are in conflict to each other. So in reality, what you do, you minimize both. And you do this with some sort of a weight, alpha, which we can play with in the code. The stronger alpha, the smoother the path. The smaller alpha, the more we retain the original points. So here's my next question. Suppose we optimize both at the same time with an appropriate alpha. What do we get? An original path, a smooth path, or no path? And the answer is we get a smooth path. To see why that's the case, let me just simulate the optimization. Suppose we're given a solution to the planning problem like this, and you run the optimization algorithm. Consider a place like this. By shifting this point into that direction, and perhaps shifting the other points in other directions, we can decrease the second arrow term, both for this pair of points and this pair of points. However, we do this at the expense of the first arrow term, since we're now shifting the point y away from the original x. Depending on the weight of these arrow terms, we might arrive at like the following. And this new path suffers an error of the first type, that we move the points away from the original points, but it drastically reduces the interpoint distance, as in this arrow term over here. If you insist that the original points are not changed, then just exclude those from the optimization. In fact, in our exercise, we will not consider those points. So y0 will always be the same as x0, and yn minus 1 will always be the same as xn minus 1, assuming we have n points starting at index 0. And the optimization is only applied to the intermediary points. So how can we optimize these two terms over here? The idea is to use gradient descent. That is, every time step, we take a small step in the direction of minimizing the error over here. So here's the expression for the first objective. When we iterate, we assign to yi recursively the old yi, but we subtract a term that's proportional to the deviation of yi to xi, weighted by a weighting function alpha that's not exactly the same alpha as before, and we set this alpha over here to 0.5. For the second term, we could implement this as follows, where we retain the old y variable, but we move a little bit into the direction of yi plus 1 and away from yi. But an even better implementation looks as follows. This is combining the step on the left and the step on the right. Realizing that each yi occurs twice in this optimization term, one here and once here, we can now go and implement this in a single update rule where we wish yi to be as close to yi minus 1 and simultaneously be as close as yi plus 1 by optimizing this combined term. Think about this a little bit, but that's what I want you to implement. And we're going to set beta to 0.1. So now let's go and implement this. And as a last hint, I don't want you to apply this optimization for the first or the last node in the sequence. I want those to be unchanged, as we'll see in a second. So here's the code I'll be giving you. There's a path in a 5x5 grid starting at 0, 0 to 4, 4. And if you look very carefully, it goes to the right at first, then straight down, then to the right again. This is exactly the path we discussed so far. It looks like this graphically. I now want you to implement the function smooth, which takes as an input the path, our two weighting factors, and a small tolerance variable, which I explain you in a second. And it creates the new path, which are the y's in our equation so far, from the old path. This is a deep copy over here. And then below the line, I want you to implement the smoother. What the smoother does, it iteratively applies the two equations I just gave you to all nodes except for the first and the last. And it does so until the total change observed in the update step becomes smaller than tolerance, at which point we consider the smoother to have converged. So here's my command. I compute a new path as a result of the function smooth. And in your test, you should uncomment the new path smooth routine and the print routine that outputs my result. Thanks for Enter, a student who posted a much better way to output matrices on a discussion forum. So I'm going to use his code or her code. Thank you so much. And here's the result. After hitting run, I have the original path over here, 0 all the way to 4, 4. The two initial and the end position should be the same as before, so please don't modify them. But in between, we get these interpolation positions over here. If you look at this, my original path didn't vary the axis at all for the first 3 steps, whereas this one goes from 0, 0, so it got closer, so it went down a little bit. And also went less to the right side than my original path. That went all the way to 2 over here, to 1.8 over here. What this means is that our new points lie a little bit like this. And as you go through the list over here, you'll find that our new points really smooth out the path to something more like that.
Hi, I'm Andy, the assistant instructor for this class, and I just wanted to provide some clarification about how you're going to use gradient descent to minimize these functions. First, I'd like to point out that there is a slight error in the path used in Sebastian's code. That 4,4 that he was using should actually be replaced with a 4,2. Also, those minus signs that you saw here should actually be replaced with plus signs if we want this gradient descent implementation to converge. Finally, even though these yi's and xi's are two-dimensional vectors, when you implement your code, it may be easier to just iterate over each individual entry. So, for example, these xi's would be these values here. One way to solve this is to define a variable called change and set it equal to tolerance, where tolerance is a parameter in our function, and you can see its default value is very, very small. And as long as this change variable is greater than or equal to tolerance, we're going to initialize change to 0 and iterate over not quite every entry in the path. You can see here that we want to exclude the first and last entries. And so for each entry, we're going to set an aux variable equal to the new path value at that entry. We're going to increment new path, where these are the equations from gradient descent. We're going to increment change by however much this new path has changed in this step. And we're going to keep doing this until change becomes less than tolerance, at which point we can return our new path. And we see if we run this, we go from this right angle jerky path to this nice smooth path taking us from 0, 0 to 4, 4.
And here's a tricky quiz question. Say we set alpha our data weight to 0 and beta our smoothing weight to 0.1, and we run this to completion. What do we get? The original path, the straight line connecting the initial and the final location, or will everything collapse to a single point? You can try this out in the IDE before answering this quiz. And the answer is a straight line. And the reason is really subtle. It's because we're not modifying the first and last point. Otherwise, it would be a single point. So I just hit the run button. And if you look at these coordinates, they go in 0.5 increments from 0, 1, 2, 3, and 4. And the same is true for this coordinate over here. So this is obviously the coordinates of a straight line as a result of our smoother applied with a smoothing weight of 0.1 and no data weight. If we change this to no smoothing weight, we obviously get the original path. So if we look at the right side versus the left side, it's now identical. So when you implement your algorithm, please test it on those settings, and we will give you a different path in our testing to see if your algorithm is implemented correctly. So congratulations, you just learned how to produce a smooth path. There's a few caveats. If you apply this algorithm in a robot world like this, where an A-star planner might give you something like this, the smooth path might then lead straight to the obstacle, which you don't want. And there's ways to accommodate this, which I just hinted. One is to use dynamic programming with a stochastic action function, and you've learned this in the previous homework assignment. That one will stay away from the obstacle. And the second one is to introduce a term that propels you away from obstacles. I won't go into any depth here, but in your optimization, you could have a term that pushes you away from obstacles by maximizing the distance between the nearest obstacle and data point. When you toss that in, you get a path that might look more like this. It is still smooth, but maximizes your clearance to obstacles. We will revisit this in the homework assignment. So let's now talk about the second part of this lesson called PID control. PID control is a vast field in control, and many classes can be taught about this one subject matter. So what I'll do is I'll give you the very basics and I'll let you implement the very basics, and I promise it'll be fun. You'll be able to drive a car around, and the Google car to the present date uses a version of this exact same controllers that's of course much more tuned to the specifics of our car. But you get to see some of the essence of what it means to control a car. So here's the problem. Consider the following car with a steerable front axle and two non-steerable wheels in the back. And say we wish this car to drive along this line, which is the output of our smoother we just discussed. Let's assume the car has a fixed forward velocity, but you have an ability to set the steering angle of the car. How would you do this? You would keep the steering constant, you could give random steering commands, or you could set the steering angle in proportion to what's known as the cross-track error, which is the lateral distance between the vehicle and the so-called reference trajectory. So the third possibility is steer in proportion to this cross-track error, CTE. Choose one of those that you think are best suited to control the car. And yes, you'll steer in proportion to the cross-track error, which means the larger the error, the more you're willing to turn towards the target trajectory. And you can see that this works. As you get closer to the trajectory, your steering will be slower and slower, and you will reach the trajectory. Clearly, the other two answers are really bad. A constant steering will put you in a circle and not in a straight line. And random steering, if you ever implement this, is a really bad idea. And believe me, we accidentally did this once. It's a really bad idea. So what you just learned is called a P controller, where P stands for proportional. And here is a really tricky question by which I want to test your intuition. One that doesn't have a unique answer, but it has a best answer. Suppose you do what I just said. You steer in proportion to the cross-track error. That is, your steering angle is proportional by some factor of tau to the cross-track error. What will happen with the car? It never quite reaches the reference trajectory. It overshoots. Or either can happen. And my answer is, it actually overshoots. The problem is, no matter how small this constant is over here, the wood eventually will turn its wheels quite a bit towards its trajectory. Then it will move towards the trajectory more and more. And when it hits it, its wheels will be straight, but the robot itself will still be oriented a little bit downwards, so it's forced to overshoot. What this means, that applied to a car, a P controller will act like this. It'll slightly overshoot, and that could be okay. The overshooting is very small, but it'll never really converge. It'll be what's called marginally stable, or often just stable in the literature. So I want you to implement such a controller. So here's the code I prepared from you. There's a class robot with which you're familiar. It has an init. You can set the position using the function set, as before. There's steering noise and distance noise. You're familiar with this. There's also something called drift, which we won't use right now, but later on it'll become handy. And there's your move command. All the way you've implemented it before. And I've improved a little bit the printout of the coordinates using floats. I wanted to implement the run command, which takes as input the control parameter that governs the proportional response of the steering angle to the cross-track error. The robot has an initial position of 0, 1, and 0, a speed of 1, and I wanted to simulate it for 100 steps. So here's what I envision to happen. Your robot is initially off the x-axis by 1. I wanted to drive along the x-axis, so the y value is the same as the cross-track error. By turning inversely proportional to the y value, using a parameter tau that sets the response strength of the proportional controller, I want the robot to turn towards the x-axis, drive in that direction, overshoot, turn around, and drive back. To do this, simulate the robot for 100 steps and use a proportionality term that sets my steering angle alpha in proportion to the cross-track error y. So enter your code here, and when you're done with it, and you run it with the coefficient 0.1, here's the output I want you to produce. It's 100 lines. You can see the robot position starting 1 off in y. It then reduces y over time to go into negative territory. On the right side, you see the corresponding steering orientation, and you can see as you move on, the y coming back into positive territory, and you can see how the robot overshoots slowly around the reference trajectory of the x-axis. So please go implement this. And here's my implementation. It's really simple. I execute the following loop 100 times. I set the cross-track error to my robot y. The steering angle becomes minus my control parameter times the cross-track error. I call the move command with the steering angle and the given speed. And I print as an output my robot along with the steering direction. So this simple routine just does it. Let's now modify the parameter to 0.3. And here's my quiz. If you modify the control parameter from 0.1 to 0.3, what happens? It oscillates faster, it oscillates slower, or nothing. Please check exactly one of those. And as we'll see, it'll oscillate faster. You have to spend some time with this, but for the larger value of 0.3, we reach a negative value in y already here, which is where we've just crossed the line. This is just 13 steps in. Whereas if we revert back to 0.1, then at step 13, we are still 0.6 off. So clearly the control oscillation is much slower and we compensate much less. So the basic next question is there a way to avoid the overshoot? And it would be nice if we could do this, because driving in an oscillating car is no fun. In fact, it makes you really seasick. Believe me, I've been in this car for months on end when we prepared for the DARPA Grand Challenge. And the trick is called PD control. In PD control, my steering alpha is not just related to the cross-track error, by virtue of the gain parameter tau p, but also to the temporal derivative of the cross-track error. What this means is that when the car has turned enough to reduce the cross-track error, it won't just go shooting for the x-axis, but it will notice that it's already reducing the error. So when the error is becoming smaller over time, it counter-steers. It steers up again. And this will allow it to gracefully approach our target trajectory, assuming appropriate settings of our differential gain tau d versus the proportional gain tau p. How do you compute this derivative over here? Well, at time t, this is the same as the cross-track error at time t minus the cross-track error at time t minus 1 divided by the time span between t and t minus 1. In our code, we assume delta t equals 1, so we can omit this. So the difference of the current cross-track error and the previous one is this term over here. And we now control not just in proportion to the error itself, but also to this difference of the error using a second constant tau d. So let's implement this. Now I give the one command two parameters, param1 and param2. And I want you to implement a controller that varies the steering direction proportionally according to parameter 1 and differentially proportionally to parameter 2. Again, run for 100 time step and see what happens. So when I run my new controller with proportionality parameter of 0.2 and the differential one is 3.0, then I get a sequence of y values that converge much more gently to 0. And miraculously, as time goes on, they really go down to 0 and stay at 0, which we didn't achieve for the proportional controller. So please write that routine so we can test it. So here's my solution. I build a variable called diff cross-track error, which is my differential, that's set to the momentary cross-track error minus the previous one, which I, in the very first time, initialized to the present one. And then in the steering, I don't just steer proportionally to the cross-track error, but also proportionally to the differential cross-track error times the parameter 2. When I put this in and I run it, it gets exactly the output that I showed you. So let's talk about a problem that often occurs in robotics called a systematic bias. And it goes as follows. When you ordered your car, you believed the front wheels were 100% aligned. But your mechanic made a mistake, and he aligned the wheels a little bit at an angle. Now, for people, that isn't a big concern. When we notice this, we just see a little bit stronger. But let's try this out with our proportional controller. So I'm now adding a line that sets the steering drift to be 10 degrees, which in radians is this expression over here, using the set steering drift command. And I want you to run my proportional controller with parameter 0.2. And for now, we're going to set the differential controller to 0. When you do this, what happens? It works just as before, or it causes a new big cross-track error. Go try it out. And of course, it causes a new error. If I go into my output for 100 steps, I'll find that the y value is between 0.7 and 0.9. So it really added a lot of error. Put differently, the robot oscillates a bit like this, with a fairly constant new offset error due to this bias. And even though the bias was in steering, it manifests itself as an increased cross-track error in the y direction. So here's a question for you that requires some thought, and you can try it out before answering this. Can the differential term solve this problem? Yes or no? And the correct answer is no, Let us try this out. Let's enter a 3.0 for the differential term, run everything, and the y error is still large. It converges now 0.87, but it's still really, really large. So what's the intuition? If you drive a car and your normal steering mode leads you to a trajectory far away from the goal, then what I submit you do is, you notice over a long period of time, you can't get closer. So you'll start steering more and more the more time goes by to the right to compensate this bias. You adjust to the bias. And as a result, when you drive, you'll steer the car this way. To do so, you need a sustained situation of large error. So that's measured by the integral or the sum of the cross-track errors over time. So let's make a new control law where steering is proportional to the cross-track errors before. It's equally proportional to the differential of the cross-track error, but now it's also proportional to what's called the integral or the sum of all the cross-track errors you ever observed. And this term is interesting. If we have a constant cross-track error of say 0.8, and the sum will increase by 0.8 for each time unit, and it'll become larger and larger and larger, and eventually it'll correct the robot's motion. So this is called a PID controller. This is the P, or the proportional term, the D, or differential term, and the I for integral, PID. So let's implement this, and the integrated cross-track error is the sum of all cross-track errors you ever observed. Let's implement this in our code. I'll give you an integral factor of 0.004, and let's not worry why I picked those. They're actually wisely chosen, as we'll see in a minute. But let's run our code and now modify your code to also allow for this parameter over here. And here's my solution. I implement a variable int cross-track error outside my main loop that initialized with 0. I then add to the int cross-track error my local cross-track error. And then I have a controller that steers in proportion to the int cross-track error. And when I hit run, I find that my y variable slowly converges all the way down to 0 or 0.05. I get even faster conversions when I set this parameter to 0.01. Looking down, you can see a little overshoot, but my controller converges to 0.0 fairly quickly and then tends to stay close to 0.0. So this PID controller is kind of the best solution for the control problem at hand. And you just implemented one. Now, here's the big question for you. How can we find good control gains? Where control gains are these parameters tau p, d, and I. Now, this is my favorite part of this class. Every one of my students has made it through it, and every one of my students is puzzled why I insist on this, but when they implement it, they get to love what I'm just about to show you. The answer is called twiddle. Twiddle is my favorite algorithm that I used in my entire life. Some people call it coordinate ascent to make it sound a little more sophisticated, but I just call it twiddle because it really gets to the heart of what's happening. In twiddle, we're trying to optimize for a set of parameters. To do so, our function run must return a goodness. This goodness multiplied by the average cross-track error. So I wanted to implement twiddle so as to minimize the average cross-track error. If that's the case, then the output of run depends on the 3 parameters. So here's how twiddle works. Build a parameter vector of our 3 target parameters and initialize it with 0. Also, build a vector of potential changes that you want to probe and initialize them for now with 1. Then you can run our command run with our parameters, and whatever it outputs is our best error so far. So now we wish to modify p as to make the error smaller, and that's where twiddle comes in. It's a really smart algorithm, I believe. We sequentially go through these parameters. Obviously, you shouldn't write 3, you should write len of p. And first we try to increase p by our probing value, compute a new error for this new modified p. If this new error is better than our best error, then we do 2 things. First, we set best error to error, and we even modify our dp to a slightly larger value by multiplying it with 1.1. Otherwise, we try the other way. So we subtract dp from p, and we have to do it twice now because we added it before. And then we do the same thing again as over here. I'm not going to write it out, but we check whether the error is better than our best error, and then we retain it and we multiply dp up by 1.1. But if both of those fail, this one over here and this one over here, we set back pi to the original value and we decrease our probing thing over here. Say we're multiplying it with 0.9. That's the core of twiddle. And what it really does is it, for each coordinate in isolation, moves our parameter up or down a little bit by this value over here. If it then finds a better solution, it retains it, and it even increments the probing interval. But if it fails to find a better solution, it goes back to the original and decreases our probing interval. We do this entire thing so long as the sum of the dp's is larger than the threshold. So somewhere in here we say while sum of dp is larger than 0.00001. It's hard to read, but I hope you could follow it. This is twiddle. So let me put this into pictures. We have three parameters, 0, 0, 0. And then in the first iteration, we bump one of the parameters up and see if it improves the error. If that's the case, we retain it. Then we go to the second parameter, we bump it up, it might not work, we bump it down, maybe we retain that one, and so on. And now as we keep bumping up, we might find that neither bumping up nor bumping down helps. So we do instead is we retain the original solution, but make our probing interval smaller than before by a factor of 0.9. In doing so, we can zoom in more and more into a detailed parameter until it finally converges. It's a local hill climber, but it happens to be really, really efficient. So to implement this, I've modified the WAND procedure to input a parameter vector of 3 parameters. And for reasons that will be obvious later, I have a print flag that I default to false. I have the same initial parameters as before. Speed and error, crosstalk error, integral crosstalk error. I set my drift parameter. And to make it a little bit more obvious what the effect of parameter selection has on my error, I'll set the total number of iterations to n times 2. And when I count the total crosstalk error, down here I only count it from step n on. So I give the algorithm a chance to converge to 0 for n steps where I don't count the crosstalk error. But I'd like to know how the crosstalk error evolves quadratically from step 101 on to 200. If the print flag is set, I set the output here in degrees and not in radians, and I return my average error, the float value. So I want you to write the routine twiddle, and the routine should find the optimal parameters and return them to me. So I want you to implement twiddle with a tolerance threshold of 0.001. When I run twiddle, it shows the parameters over time and the crosstalk error, and this crosstalk error very quickly goes to 0. In fact, after a few iterations, 107 in my implementation, we get a crosstalk error of 3.611 to the minus 17th. And here's a typical control run. You see my x, my y, my orientation. My drift is constant. That's my constant drift parameters. And in the beginning, the error is 195 on average. But after a short amount of time, you'd find that my y error goes down to 10 to the minus 6 and stays there, which means our controller is really, really good in tracking our desired location. And our final control error between time step 100 and 200 is 3.611. So I wanted to implement twiddle. We might change something on the robot setup, but when you run it, it will be such that if you run a full PID controller and find the optimal parameters, that the final control error will be really, really small. And that's what we'll be checking. And here's my implementation of twiddle. This is a routine that you can keep this way for many, many different applications. All it requires is a way to evaluate something that depends on the parameters and gives you a single error that you'd like to minimize. We have 3 parameters in total. I set the parameters themselves to 0, but the deltas to 1. And it's just a counter, it's unimportant. If the sum of dparams is still larger than our tolerance, which we initialize with 0.001, then I go through all the parameters sequentially. I increment it by dparams, find out what the error is. If the error is better than our best error, which I initialized with the initial error, then I keep the best error and I even increment dparams. Otherwise, I try the other direction. Run, find out the error. If that succeeds, I keep it, I increment dparams. And here's my last case. I didn't succeed, so I'm going to set it back to the old parameter vector and decrease my dparams by 0.9. I increase my counter. Here's my little printout command for debugging. and I return the parameter vector. So let me comment out the print vectors over here and play with this a little more. If I run twiddle, compute the best parameters, and then calculate the error using these parameters, and print out the parameters along with the error, I get a parameter vector, and I get an error that's basically 0. Now let's switch off the integral term. And I can do this with a little trick. I just set the params number 2, which is the final one, to 0.0, as if I already learned the integral term. When I run this, I get a 0 integral term, but an error that's somewhat larger than the final error that I desired. And that's because the integral term is really required to drive the error down to 0. Let's also remove the d term and see what happens. And the result is a really large error of 0.55. That large error sustains even if I remove the robot drift by commenting it out. We still get an error of 0.10 if we just have a proportional controller. Whereas if I add in the differential parameter again by removing the dpram1 command, the 0.103 goes down to 5.7 to the minus 11, which is practically 0. So you can see the importance of the d term for driving the error down to 0 in the case without drift, and for the integral term in cases for robots with a systematic bias. We play a little bit more with this code for the homework assignment, but this is it for now. Let me summarize. You learned two really important things that we use every day in robot programming, and they were somewhat complementary. First, we talked about smoothing, which took a discrete path and turned it into a continuous smooth path. And then we learned about how the robot can follow this smooth path using a control mechanism called PID. With this, you can actually implement quite a bit of robotics. Well, no matter what robot you have, apply a planner, apply a smoother, apply a controller, and it'll do just fine. In fact, this is about the level at which our DARPA Grand Challenge car won the DARPA Grand Challenge. The Google car itself has a little bit more juice in it. It considers the case that the steering wheel itself is inertia and that the steering wheel is driven by something called torque, not by position. But leaving this aside, you really got a gist out of what's happening in robotic driving. And now you're able to really control an actual robot. Congratulations, that is really, really cool.